Okay, thanks very much for the introduction, the opportunity to speak here. So my talk is about learning random dynamical systems, and it will contain two parts, my talk. The first is that I will talk about random dynamical systems a little bit, give a bit of a pitch of what I'm actually trying to do and why am I trying to do this, because there are not that many people that study random dynamical systems, so I'd like to make a pitch for that. And then secondly, I'm trying to kind of see how we can learn such things from time series data. So this is joint work with Emilia Gibson, who is doing a PhD with me at Imperial, and clearly much of the credit of the learning iterative function systems, which I will talk about in the second part, goes to her. Good. I like, just because I'm not a data scientist, I like to remind myself normally what it is that I try to do. So, in my view, data science is about inferring some facts from data, but data are just backup numbers. So intrinsically, the backup numbers has no meaning, it's just a backup numbers, and we want to learn something from that. So how do we learn something from a backup numbers? Is somehow to imply some kind of idea that it comes from somewhere, and there's a model. So any kind of data science algorithm has a model behind it, even those that are supposedly called black box, because even in the black box, and maybe people don't know what's in the black box, but there's something in the black box called a model. That's how it works. Yeah, so the choice of such a model is very important, because depending on which model you use, you can actually learn something or maybe not learn something. So I think it's very important to think in data science actually to first ask about what question do we want to answer, and then try to design a way to maybe extract this from observations, if you understand which observations we have, and not to first start with observations, then have a generic model, and then try to answer some questions. And there's a good chance that these questions are just unanswerable based on the model you used or the data you have. Yeah, so I think it's a very high level comment, but I'm just amazed how I see a lot of people talking about some kind of like general settings, which to be very hard to understand. So one important thing from the mathematics point of view, I believe, is that how we learn things from models is because they have some structure. So mathematical structure is important. And that helps us to then identify objects or things or means by which we can do computation or something else. So mathematics is intrinsically important to data science. It's not a small thing. So I tell this especially to funders that need to fund us to help data science people do a better job. Yeah. So this is not widely accepted, unfortunately. So there's many people that don't simply know this point, including mathematicians. And then my point is also that structure somehow is key to the interpretation and meaning of model data. This is maybe, in some sense, the structure of the model is already a starting point somehow. So, and I hope that I will make this point across about what I'm trying to do. Okay, so learning dynamics, the starting point that I'll take here is that I have a time-ordered series of observation of some system. And objective one is to learn some kind of evolution that's consistent with this observation. Because I presume that the dynamics is something that evolves in time, but I don't really have all possible observations in time. So I have only a fraction, I have some sample, and I want to kind of learn some evolution. So of course I can never learn the evolution, I learn only something which is consistent in some sense. With the observation, there's a lot of choices. Now, an objective two, which I will not talk about here, but which is very interesting, is actually try to learn something about dynamics without learning evolution. I think it should be possible to learn things about dynamics, which is not the evolution equation, and maybe that's more reliable or faster. For instance, we want to maybe learn does a system have chaotic behavior or something like that? And the question: do you first need to really estimate the equation of motion, and then through this equation of motion hope that you can understand this, or are there some objects that you can extract from data or from models that actually will give you some intrinsic information? So that's why also this mathematics is very important. Are there shortcuts? Are there some things you can understand without just kind of like basically simulating up to infinity some learned evolution equation? That doesn't seem to be a really smart idea. Yeah. But there seemed to be a huge effort in learning evolution equations that I will talk about in this talk. So model choices, if you do dynamics, then of course we can think of like, well, how is my dynamics generated? Well, it could be by ODEs, by PDEs, by stochastic differential equations, stochastic partial differential equations, by some diffeomorphisms, or we can think of transfer operators, or there's lots of things we can think of. And all of these models have some advantages and disadvantages, and ability to answer certain questions or not. So again, one should be careful about that. I don't think it's wise to make a choice before you know what you want to do. And there's different techniques for these things, as long as you understand how these things are set up. So my proposition here is that I want to learn so-called a random dynamical system. So I put this here in red because it's not on the list above. And I think it's a very type of generic model, which could be very useful. There's a certain drawback that it's very hard to find a textbook that tells you what to do, and also they don't also what to do if once you have found this random dynamical system. So ODEs are nice because we know how to analyze ODEs, and not just by simulation, but we have some kind of like good strategies to understand them. Maybe PDEs and SPDEs, and so SDEs we have some techniques and so. So there's in several settings there's kind of like enough knowledge about these models that we can do something smart with them. So it's actually advantageous to maybe learn them. And random dynamical systems is a bit in a corner where I think it shouldn't be, is that it's not so often used. But I'm trying to convince you differently. Okay, so what is a random dynamical system? In my view, that's a special case of a so-called non-autonomous dynamical system. So autonomous dynamical system is something which is time independent. And so what's the history? Of course, it's like, celestial mechanics, all this, big motivators for dynamical system theory is like, we believe that the planets move, and that the laws of physics that move the planets are not so dependent on time. So and so this was a big motivator for doing dynamics. This is autonomous because there's no time dependence. But if you look at dynamical systems relevance for the world around us, I would say most of it is non-autonomous because there's very few things that we can put things in a box and say we just wait till the end of the times to see what happens, and we just have no external influences or not even changes of the rules. And so usually autonomous is basically some kind of approximation of reality, but not always valid. So if it's very non-autonomous, then you have things like control theory, and people are very interested in steering cars and steering everything, steering the economy. And yeah, that's also that direction thing which people should invest more in. This connection between dynamics and control should be, of course, obviously more explored than it is. Anyway, so we think of this non-autonomous system as a skew product. I think of something that's non-autonomous, which is basically driven by something which depends on time. So I write these first equations in a slightly more general way as a function where on the top equation where the brackets are here, I call this sort of fiber. I think of it as a fiber bundle structure, and this is called the base. So in the base is my noise. I model my noise in the base. It has an evolution, and I wrote here that it's just basically, well, or it's a non-autonomous system. Sorry, it's not noise necessarily. It's anything that drives this system, but there's no coupling back from the x variables to the u variables. It's called skew product. So it's master slave. People use all these kind of terms. So there's something that's independent of x. There's the u, and that drives the x equation. So there's many contexts in this. So the dynamical systems theory for this is poorly developed, unless maybe this base dynamics is say periodic or something like that, because then it's almost autonomous. Anyway, that's another story. But what can you do to make something? This is actually hard to do in general. But what's nice if you put some more structure on this base, that we have some probabilistic theory there, then it helps a lot. So we have an additional feature that puts some probability in the base, and that gives me opportunities to not just have an unwieldy set of non-autonomous systems, but I can maybe say that some are more likely than others. And so hopefully I can make some statements to say like maybe almost surely something happens, maybe not always. So I can throw away a measure zero set of realizations in the base. That turns out to be very, very useful using theoretical techniques from ergodic theory and stuff like that. And so here is my then setting. It's a random dynamical system. It's a non-autonomous skew box system, whose driving admits some kind of probabilistic description, for instance, through ergodicity invariant measures. And so, for instance, the simple example is where we have a mapping, which should be xn plus 1, sorry, should be n plus 1. Here's f of xn un. And where un is just basically some output of some Markov process. So I have equations of motion that change every time the un changes value, then they have a different rule. And but an SDE is another example. It's not so obvious, but an SDE can be thought of also something where you basically drive here. This is additive noise. I just drive it with some process here. And of course, this is not so nice, but in this specific case, it's very nice because you can see it's like driving, unfortunately, by continuous functions. But the Wiener measure that's important there is such that it put full measure on continuous functions which are not differentiable. Yeah. So that's where we come. So that's an artifact somehow of a continuum limit of something. Yeah, so you can think of, and then you of course have to think about integration means, and that's how stochastic calculus has certain solutions to that problem. So basically this is also a driven system. So an SDE is just a special continuous model with a nice base dynamics, which is Markovian, and the price you pay is that you get these ugly looking generic noise realizations. Yeah, but in principle, all realizations are allowed. It's just that the smooth ones that measure 0. Good. So how do people usually deal with this kind of things? So most people study random dynamical systems in the SDE context, although they don't do much dynamics, and I'll talk a little bit about this now. So in the theory of the stochastic processes, and also ergodic theory of dynamical systems, there's some preference to consider the problem of so-called one-point Markov process associated to the random dynamical system, SDE, or even the deterministic dynamical system. And that leads to study of transfer operators, Markov semigroups and stuff, and it gives some kind of probabilistic model for the time series of the system. So what it gives is so some people write an SDE and they say, well, this SDE is basically Markov semigroup. It's fine. You can think of it like that. You can also think of it like that. Well, I think of the SDE as being motivated of something which is really path driven. That's my preference. And then of course there's a realization of the paths, and they have additional information. You can also put the topology, for instance, on these functions. You can say two functions are close to each other. In the strictly probabilistic setting, that's cursing loudly in the church of probability. But yeah, in the dynamical system setting, it's very natural to do that. But what you do is, just have a model for time series. So that's not like dynamics like you have, for instance, in celestial mechanics, where we know not that you only have, say, one, initial condition leads to some kind of a quasi-periodic orbit. We know that nearby orbits also have all kinds of properties. You actually have some kind of consistent model where different initial conditions are coherently kind of moving forward. So in this one-point Markov process, you don't have that. You have no information. You just have information of one particle only. So if that's what you're interested in, that's a great model. And the nice thing is that, of course, it makes these models much easier. So when I only look at just one trajectory, I want to do the statistical description of one trajectory. It's much easier question than say what happens in general in the phase space with all possible initial conditions. Yeah, so it's a different question. And good, yeah, so stationary measures are basically kind of invariant measures of the Markov semigroup or transfer operator, and they give you, through Birkhoff-ergodic theorem, lots of statistical properties. So some questions can be asked like that, answered like that, but not all questions. Good. So dynamics of random dynamical systems. So importantly, if you think of the random dynamical system, it contains information that's not contained in this Markov process, in this one-point Markov process. But possibly it's really important. For instance, anything that's related to endpoint motions, where n is larger than 2, that basically I look at pairs of initial conditions and see how they behave. You can think, for instance, of initial conditions. You just have two initial conditions close to each other, and then they move away from each other. So even separation of trajectories, of course, is not described by the one-point Markov process. It's impossible to, because it only has one trajectory in mind. But you may ask, like, how, if you start with two initial conditions, how often do they come back to each other? For instance, what kind of like properties do they have? So it's initial dependence, sensitive dependence on initial conditions, chaos, and also pathwise statistics, for instance, quenched statistical properties on time series. You can, for instance, ask like the decay of correlations, for instance, along paths. Good. So 3 papers, a little bit biased. It's from people in my group. This is myself and students, so I apologize for that. There are, of course, some other works as well, but here's some 3 examples. For instance, we identified that chaotic dynamics has some kind of like random version of horseshoes in the back. So this is known in deterministic systems. So by a result of Katok, a famous guy in that field, says that basically if you have some kind of chaos, positively outcome exponent and recurrence, then you can build horseshoes. Horseshoes are transverse intersections of stable and unstable manifolds. That's a paradigm model, but it's also the other way around. So in the random setting, you also have these things, but now, of course, everything is a little bit different because we don't have periodic orbits, for instance. Random systems have no periodic orbits. They have random orbits. So, but they still make up things that look similar, and they topologically, it's a topological aspect of the dynamics. So there's the things that are usually associated with chaos are really there if you have positively outcome exponent in random systems. And then Matteos and Giuseppe did some stuff on this the exponential decay of correlation for the quenched process. Quenched process means that look like pathwise. And then recently, also with Alian Homburg and Vincent Goversen, Vincent's also a student, we looked at the transition of negative to positive Lyapunov exponent, and I'll refer to that, and give topological dynamical properties of this. So not just probabilistic. So that there's the nice thing about doing non-autonomous dynamics is that, yeah, you put some measures on it, but not everything is just statistic. It's not just only talking measure space. You can just analyze topological properties, but you can maybe look at topological properties which are true almost surely or something like that. So, but you don't need to do just measures. So we found, for instance, that we have sticking behavior, intermittent behavior, precisely when you have a transition from non-chaotic to chaotic dynamics in random systems. And this is overall quite different than say, the roots to chaos that are known in deterministic dynamics. Yeah. Anyway, I just, this sounds very general, high level. So let's just look at some examples just to kind of set our mind of what goes on. Here's an example of a differential equation, which if you have no noise, sigma 0, then it has Hopf bifurcation. So depending on parameters, you either have stable equilibrium in the center, or you have an unstable equilibrium and an attracting limit cycle. And now you can put some noise there, and you can ask what happens. If you put some noise there, then this is one of these examples where you can actually just solve for the Markov-Simi group, because it's a Fokker-Planck equation and it has a potential, it's a gradient system. You can just kind of solve it, and here's the explicit function of the density of the stationary measure. So the explicit formula. So we say in very good territory. It's just textbook. And there's an interesting thing. There's a parameter B here, which is shear, and this doesn't appear in this formula. So there's one parameter I can play with. And so what I'll try to argue is that if I play with the parameter B, my dynamics changes a lot, but the stationary measure base stays exactly the same. So if I look at the Markov, the one-point Markov process, the statistics of that is basically all completely driven by this stationary measure. It's independent of B. So here's the picture of the stationary measure on the top, and on the bottom is a sketch of the phase port. Right? So we have an attracting equilibrium, or we have an attracting limit cycle and a repelling equilibrium. It's just as simple as it gets. And then you put some noise on it, and you look at the stationary measure, and it has here the density, and you see some nice picture. It's kind of, either the measure is concentrated on the stable equilibrium, or it's concentrated on the limit cycle, nice circle. Yeah, no problem here. But now if you do dynamics, then I'm going to do the following experiment. I'm taking a whole bunch of initial conditions, like 1,000 initial conditions, and just run them forward. And I stop the time at t is 50. And so in the top picture, what you see is almost not visible. There's a point here. So all initial conditions converge to the same point. We call it synchronization, a noise-induced synchronization. And this is for B is 1, so low shear. If I make the shear very high, B is 20 here, sorry, then I get some shape which looks a bit like strange attractor. It looks a bit like people maybe know these things like a Hinnon attractor or something like that. Something with kind of strange, funny. So what it means here is that here, I run it by one noise realization, different initial condition. It means that where the points go doesn't depend on initial condition. It only depends on the noise realization. Of course, if I change the noise realization, I go to a different point, but all the points go to the same point. Here, there's a distribution where all these initial conditions, they sit on some kind of complicated object. it turns out to have fractal properties. And so there is not a unique location. It is concentrated on something which is an attractor, but this attractor is non-autonomous. It's time dependent. If I run time forward, this object is going to change. And so here we have negatively Lyapunov exponent, for instance, and here positively Lyapunov exponent. So here sensitive depends on initial conditions, and here not. But the stationary measure is exactly the same. Now you're going to tell me that it doesn't matter. Of course it matters for the dynamics. Of course it matters for properties. So there's a very different dynamics going on in one system and the other system. But they have the same statistics of one-point motion. So here's a movie of this evolution of these many initial conditions. This is made by Dennis Chemnitz from Berlin. And you see here what happens somehow. So you get some kind of convergence to a non-autonomous object, which is a non-autonomous attractor. It's a random attractor. But it has very nice properties. It has very stable geometric properties. Yeah, so we'd like to know about such things, right? And the blue circle was the deterministic limit cycle in the background, which has not much to do. Yeah, so you see here that what it looks like. So I took this a snapshot at some long time, but in principle, what you see is some convergence to an attractor which is non-autonomous. Yeah, so this is what random dynamics gives you. It's a special type of non-autonomous dynamical system. Okay, let me go back to my slides. Good. Another aspect that I'd like to show you is that this sensitive dependence on initial conditions, how that works out, and you can actually measure it. So here's another example where we have a system with two limit cycles. One is attracting and one is repelling, and the origin is also repelling, and this is associated potential, and you can also here compute stationary measure by hand and stuff like that. But there's some interesting behavior going on here, and I have another movie that actually makes a point here about the dynamics. Is this one. So here what we start with two initial conditions close to each other, and the red loop is the unstable limit cycle, and you see what happens that these two initial conditions are getting attracted to each other. And they happily stay together. So it's a little tail represented. That's why you can see the point moving. I give it a little tail of the past, and it moves around within the circle. And once it gets outside this circle, suddenly you see these trajectories. They are now separating. You see. So there's some kind of behavior here where, as long as I stay inside this red circle, my trajectories will stay close to each other. When I go out of them, they get separate. So this is associated with what we call the conditioned Lyapunov exponent. It's something that's theoretically very well defined. And it basically says that as long as you stay inside the circle, you stay close to each other. But if you're outside the circle, you deviate from each other. So the general one-point motion theory of the Lyapunov exponent would say that we have a positive Lyapunov exponent for the whole system. It will not reveal that you have actually local behavior where you never separate the trajectories when you're in the first thing. So these are kind of all aspects of random dynamics, which I think are obviously interesting and relevant in some settings, which are just not studied, and definitely not studied in normally by people doing, say, stochastic analysis of these equations, because they basically look at stationary measures, doesn't tell anything about these kind of behaviors. Good. So now I want to switch to this learning. So my motivation to learn random dynamical systems is that I'd like to learn these models that then can inform me about such behaviors. Because if I learn an SDE, or I learn, say, transfer operator, so Markov symmetry group, I don't learn these kind of things. I already cannot learn anything about it. I cannot answer any questions about these dynamical features. So here I'm going to look at what is one of the simplest examples of a random dynamical system. It's a so-called iterated function system. So I'm thinking of a random system where I only have a finite number of transformations, and I'm going to operate this finite number of transformations in a random way, but I'm going to assume that this is done according to some finite state Markov chain. Yeah, so I have k functions, and I think of a finite Markov chain on these k functions. So there's a transition probability for each of them to each of the other ones, but maybe some of them are zero, whatever. And I then can operate these random systems, because of course what I do is I pick a realization of my noise. My noise is just a simple sequence with symbols in between 1 and k. And then I just execute this, and the question is, what do we see? And can we learn this system? Can we learn the functions f1 to fk from observation of the system? And can we also learn the underlying Markov process, given that we know that's a Markov process? Okay, so we think of this as a random system, but because the noise is just basically the shift operator on symbol sequences, right? Because noise realization is picking the sequence of maps. It's just basically you can also kind of like think of the base space as a space of all symbol sequences with symbols between 1 and k. And then the dynamics is just shifting this one forward because every time I pick a new realization from this noise. I make it double-sided because that's a nice setting, but it's not relevant actually for what I'm talking here. Good. So what kind of data could you see? For instance, these two pictures. So first picture is the Sierpinski triangle, and the second one is, I don't know, some mess. So there's two examples. So the first example is very well known. Maybe anyone here knows it. It's not a class, but maybe it's a good question. Does anyone knows the dynamical system that generates a Sierpinski triangle? Okay, there's a book that was very popular when I was young, by Michael Barnsley, Fractals Everywhere. And so this book propagates precisely things. These are kind of like stochastic so iterative function system. So you take 3 contractions, one that take this whole triangle into each of the corners, contracts it by a factor of 1/2 and puts it in a corner. And if you do a random composition of these contractions, you get very nicely this kind of fractal Sierpinski triangle. Sierpinski triangle is a fixed point of this random dynamical system. And so how can you actually do this? This is a composition of 3 contractions, and there's some theory that says you can. He has this whole story about how you can learn photographs and make them all attractors under some finite set of contractions. And so you need to look at the invariance properties of the invariant measure, and then you can learn next to contractions are generated. And so here you can see this picture is self-similar with respect to these 3 contractions, and that's why it generates precisely this picture. It's a unique object. Okay, the underlying theory is ergodic theory. It says for almost any realization of the base dynamics of the simple sequence, this is here 3 maps, you will get this picture. On the right-hand side is yet to be disclosed thing. But the question is, I cannot just learn the dynamics and everything from this data. So in some sense, Barnsley has already something about his left-hand side. If it's all nice contractions, disclosure, the right-hand side is not contractions, not so easy to figure that out. There's also linear contractions on the left-hand side, makes everything a lot easier. Good. So the first task, which is the relatively easy one, is learning a fully observed iterative function system. So I now presume that I have this whole picture. I have this picture, and I'm given the fact that actually the data that's of relevance is precisely this 2-dimensional data, and that it's a mapping. These are mappings from R2 to R2. So then what I basically need to do, I need to learn the different functions that make something up of this. So I need some assumptions because otherwise I can't do anything. So that's basically the structure of the model. I assume that these functions are smooth functions. So I will explain later why. So what happens then if it's smooth functions? I can plot the data xn to xn plus 1, and I should see, if I look at the picture, here's a picture from R2 into R2. So it's like a 4-dimensional picture, can't draw it really, but it should give you some kind of graph. It should give you a graph, a 2-dimensional graph of R2, which will say what these functions are, because it's a function of two variables into 2 variables. So how can I learn a function? Oh, it's like manifold learning. I can say, well, if it's a manifold, we have to try to fit a manifold through this function, and hopefully have enough data for this. Yeah. So in principle, you can do that, and you can then do a cluster algorithm. Now, the tricky point is that because I have many graphs at the same time, these graphs could intersect. So I need to have some. So what we do is we just look some differential topology. We think if they're we look at the notion of transversality, and we try to separate when we cluster, we try to kind of like use transversality as a guidance on how to choose how things connect together. So it's a clustering algorithm using some transversality assumption. You need some assumptions, otherwise you can fit everything to everything. Good. So then we get a multi-manifold, and we can actually separate those things. And then once I have these different mappings, then of course I can now look at transition probabilities because I still have my dynamical data. I can say, how do I jump from one graph to another graph? That gives me transition probabilities in the Markov chain. So here's an example, for instance. So this is a projection because we have two-dimensional graphs over R2. Here's a projection in the R3, so it's only the one component is drawn, and this is on the data. So basically these are different planes, but all this data sit in a plane. You can actually learn that the plane fits very well. So you learn precisely these three contractions for the Sierpinski thing from this. It separates the data very nicely. And here's another example, a Polonian gasket, which also is an iterative function system, but now it's a bit more complicated. It has some complex function. It's in the complex plane. So two operations are just rotations over 120 degrees. And I think there should 2 pi divided by 3, not times 3, sorry, in the exponent. And there's some complex functions. This is well studied in complex dynamics. And you can actually kind of separate these things off. So you can learn the relevant mappings from these surfaces. And these surfaces, they lie basically on manifolds. You can estimate these manifolds. So this is not so hard. And here's the other example. Sorry. Yeah, so I learned 3 different graphs. I cluster the points, and I figure out that there are actually 3 different functions operating. So I try to kind of cluster the points in a consistent way, using some algorithm that clusters them, and then I find that's actually there are 3 manifolds on which this lie. So first I cluster the points, and then I extrapolate the function. I know the function in these points, and I try to make a nice fit. Because of course I don't where are the gaps, I don't know it. I don't have data, but I try to make a smooth fit by whatever method. You must of course make a bias to do something which is relatively nice and doesn't make crazy stuff in where you have no data. Yeah, so I learned by clustering, clustering in the tangent bundle, because I use derivatives as well. So these manifolds, even if they intersect, they lie far away if they transverse. And I cluster the points, put the points together, then I learn manifolds. But that's relatively easy, and it works well. And this was the other example, the black pictures that I showed you before, and it happens to be 2 Henon maps. It's 2 Henon maps with different parameter values. They're here on the bottom, that are iterated in some random way, given some kind of transition probabilities on this 2-state Markov chain. Okay, here's another example which is a little bit nicer. This is a 2-dimensional example where we have just linear contraction plus some translation, so it's affine. It's and you see also here nice separation in terms of these 2 maps, in terms of projections of these manifolds. Good. So the trickier bit is to learn partial observed dynamics. And we are trying to kind of employ delay embedding. So when we're learning dynamics from the time series, sorry, I sometimes have the tendency to preach a little bit, but I think sometimes necessary. So there's a pre-assumed property of that the to-be-learned model is that it's Markovian in some sense. Markovian in the sense that if I know the state of the system, I can predict the future. And that's really essential that you have to assume this. And of course, all our models from physics and most models that we use, they are like that. But we are not guaranteed, if you look at the time series, that is the case. So even if you want to learn a Markovian model, a dynamical system, I think it's good to check. You can check these things. You can check whether nearby initial conditions give you almost the same answer. If there's some kind of continuity, if there's some kind of hint of being Markovian. If it's definitely not Markovian, you shouldn't never treat it as Markovian. You can fit any Markovian model to any data, no problem. You just get really weird and bad models. Yeah. So being Markovian is really an assumption that you have to put in the model, but you can check it on the data where it's relevant. Anyway, so that's one comment. But the other thing is that if you have a partially observed a Markovian system, which is in essence not Markovian, is partially observed, then we know that we can make delay coordinates in delay version, that we can actually see a Markovian model in these delay coordinates, which is equivalent, even essentially conjugate to the original system. So that's very nice. So that's what people do. People call this delay embedding, something called Tagas embedding. And it takes account the history of the state. So it's the information that you don't have, you can basically recover. So there was an origin in the Markovian model you can recover by taking history into account, and somehow it gives you enough information. and that needs some kind of embedding dimension that has to do with some Whitney theory of projections in the spaces. Anyway, so what are we now trying to do? We try to do this also with the iteration function system. So I now assume that we have some observable that's not observing the noise. We're never observing the noise, but we just observe things in the state space. So here, nu is my observation function, and I'm just gonna, take the whatever the system is and observe the Zn. So I have time series to Zn. It's given by this equation, and then I'm trying to apply a delay embedding for the partially observed iterating function system. Now, what's really important now is that once we go through the dynamics, if we go to the delay, then let's take the history into account. But what's important for the dynamics is that there was also a history of the noise. So depending on the history of the noise, there was a different type of evolution. So if I take a delay of length 5, then I have to take account of all possible noise realizations. I call them time 5. And that gives me different dynamics. So I get, in the end, a system which, if it's properly representing something, will be some kind of iterated function system, but it will have many, many more different functions, because the function depends on the past. Because my delay factor depends on the past, the noise was going through the past. So I don't have independence. So I get some kind of blow up of the number of states from this thing. So here's an example. So we have a system with two transformations, but now if I take a delay of length 2, I can get 1, 1, 1, 2, 2, 1, or 2, 2. I get 4 different types of evolutions out of it. And you see here that if we learn from the data the manifolds, then we get 4 manifolds, depending on 1, 1, 1, 2, 2, 1, and 2, 2, as noise realization over these two, because the noise is only a sequence in 1s and 2s. Good, so now, of course, I can learn these functions. I can learn the functions associated with 1, 1, 1, 2, 1, 2, 2, 1, and 2, 2. But I don't really want to learn that delayed equation. I want to learn my original iterated function system. I want to learn that it was not something generated by 4 maps, but by 2 maps. So how do I do that? How can I disentangle this Markov chain? So I can, of course, also learn probabilities and so associated with this, just like before. So using the clustering methods, we identify these functions and with relevant transition probabilities. But the task is really to kind of like see how we can invert this this Markov chain into something which is smaller, which will reveal that we were actually originally having only 2 maps and not 4 maps. So the task is the following. We have the right-hand side Markov chain with probabilities, and you want to derive. So this is the Markov chain. That is precisely, if you look at the left Markov chain, I take steps of length 2, and there's 4 types of these steps, and I take the transition probabilities. I can just compute from the left-hand picture the right-hand picture. That's kind of easy, just by taking paths of length 2. It looks a much more complicated Markov chain with more states. But I want to do the inverse. I want to recover this Markov chain. So this is possible by some combinatorial algorithm in general. That's very good news. That means that in principle, once we have this complicated Markov chain, I can recover the original Markov chain. Good. So the algorithm is due to Emilia. So it has some non-trivialities in it, which I will not talk about now. But this is the wrong slide. So once we have identified the structure of this integration system, we also want to learn the representation. So what I learn now is I have a number of functions. I can have a Markov chain. I invert it to the smaller Markov chain, but now, of course, I want a representation of mappings in the original chain that generate data that looks like this the right model, right? So I don't want to stick. Now, you may think like, oh, what I just need to do is I need to understand that these composite functions that I have are just compositions of other functions, and that doesn't work because of the involvement of the noise. So it's not possible in the delay embedding to say, well, all these functions that I have there, they're just compositions of some other function. That doesn't work because everything depends on time. So it's not, yeah, you cannot just compose every function with any other function. It depends on how they develop. So that doesn't really work. But what you can do is when you notice the Markov chain structure, you can go back to the original data, and then you use basically an embedding theorem for each of the individual maps that you have, because you know how many maps you're supposed to have, and you know where they're coming from. And you can actually then learn this by, not by delay embedding, but just hidden variables fitting. You can actually reconstruct a mapping which generates a model which is entirely consistent with the observations, has the right iterative function structure. Yeah. So there's some do's and don'ts. So there's some things that cannot be done, but you can still, you go back to the chain, you learn the Markov chain, you go back up, and then you construct the mapping. So you don't construct them directly from these composite mappings because they're complicated. Good, so this yields a model that's accurately represents the IFS and the observations, but of course there's a choice of these hidden variables yielding intrinsic symmetry group of diffeos in this construction, because hidden variables, you don't know which hidden variable to choose. You just say, I only observe something from a certain dimension, the other dimensions I don't know. I could choose coordinates there in any way I like. So if you learn, here's an example where we have Apollonian gasket on the left-hand side, and what we learn is a dynamical system, an iterative function system with 3 maps, but it then has some kind of diffeomorphic, it's a diffeomorphic image. So that's something that you cannot recover, that's what you don't observe. So if you only observe partial observation, you cannot really guess what are the coordinates, but you get the right structure out of it. It's just not exactly the right one. Good. So here again, here's the partial observation from the Henon map. So hard to see any structure in that on the left-hand side. This is just the time evolution of one of the coordinates. But if I put in my mind that it may well be an iterative function system, I can learn from this partial observation here, these 4 mappings. But there's actually there's only 2 Henon maps that were used. So then I have to kind of understand that the Markov chain here can be reduced to a Markov chain of only 2 elements. And then I can learn also here, I can learn these Henon maps very accurately back. So I think what I show here is that actually I have a model with a certain structure. And in order to learn this structure from observations, I really need to know what I'm looking for somehow. I can't just kind of throw some data in the air and say, let's fit it. If it's very naive and just fit a curve, fine. But if the model has some structure, I need to take the structure into account, right? The structure gives you some meaning to the model. It can then conclude things about the model. So if I just say I have some data, let me fit this data to some function, I get, of course, all kinds of models that may do something, but they will not be able then to give me the information that I wanted to. But that goes back to the philosophical point I made in the beginning, that I will have to kind of ask myself, what do I want? If I want a random dynamical system potentially to understand details of the dynamics, I need to make a lot more effort. I need to assume some structure. And of course, it could be that the data just tells me the structure isn't there. Fine. Then it just says, this is not a good model for this data. But you cannot just say there's some generic stuff. At least I don't see how this could work. And this is just one example of another type of model. Many other types of models could be made. And it is very insightful because once you look at it from the right point of view, a lot of structure in the data is revealed. If you don't look from the right point of view, you see nothing. Good. So the outlook, of course, is that this is just a pilot study. We want to do much more general classes of RDSs, like the ones that I study with my other students on the dynamical systems part, including also continuous time models like SDEs, but maybe also other type of continuous processes, and apply this to discover RDS models from data, especially in complex systems. So there's a huge opportunity to model, especially complex systems, with something which is a combination of some probabilistic driving on top of some things. There's many examples where this is well known. For instance, mean field models where the mean field is not exact at all, means you have a lot of fluctuations, that you think that the mean field that's driven by fluctuations. There's many other high-dimensional systems that very much look like low-dimensional systems with some noise. And the low-dimensional systems are much better interpretable than the high-dimensional systems. So it's a very good model to make some sense of things if it fits. And so my expectation is that if you look out of the window, a lot of things that we find very complicated look like low-dimensional random dynamical system, where some features are very described by the nonlinearities of the low system, and the noise is not small, but the noise is interpretable somehow in terms of this context. And I think that would be really great, because then there's an audience for the random dynamical system theory that I developed, which I think obviously should be part of the lingo of mathematical modelers, but it isn't. so much at the moment. So one of the reasons, of course, why this is difficult is because, you know, in the past, people do things by hand. More general random numerical system models other than SDEs, I don't know you can do anything by hand. So there's no like simple model where you can just solve things by hand. That stops you from developing things. That's just the past. The past was like that. If you can't do it by hand, don't do it. At least there must be some simple examples you can do by hand. If there's no simple example you can do by hand, it's just not done. Yeah, but it's a huge opportunity to do these things. And then, yeah, so this is work with Emilia, and yeah, we will preprint before SciEM. We have a preprint. Okay, good. Okay, thank you very much for your attention. And
so this is a joint work with my student, Nicola, who, as I mentioned last week, is finishing this year his PhD, and now is going to work for a startup in California, at least for the summer, implementing some of these things. So I guess that's a good sign. And yeah, so the starting point, as the title suggests, is you know, a deep learning architecture that is quite famous nowadays, which is a transformer. And the core operation of a transformer is the attention layer, or the attention mechanism, which was introduced in 2017. And since then, it had major successes in sequential data processing. And so transformer, in its most simple form, takes in an input sequence of length capital L, and forms three separate vectors, which are called the queries, keys, and value vectors, by simply multiplying each element of the sequence by a corresponding matrix, which are called keys, queries, and value matrices. And then it averages the sequence of values. It does a weighted sum of the sequence of values, where the weights are given by these softmax weights. Okay. So some communities know this as an Adarayama-Watson filter, I'm told. This, you know, if you think in terms of probability, this is a change of measure. But then, you know, in deep learning, this is attention. Okay? I mean, this is nothing special. It's just a reweight with a given weight of the input sequence. Now, if you stack the, sorry, this is too loud. If you stack the queries, keys, and values vectors into a single matrix, you get three matrices, capital Q, capital K, and capital V, sorry. And you can rewrite this, you can essentially vectorize, if you want, this operation, and make it look in this form, right? So the output matrix is simply equal to this linear algebra operation, which involves only matrices. And this is exactly why this architecture or this mechanism is mainstream in deep learning, because it can be parallelized on GPUs, because it can be written in this way. Now, the problem is that the computational cost of this operation is quadratic in capital L, in the length of the sequence. And so it's true that it can be parallelized, but it has a quadratic cost in the length of the sequence. Now, to mitigate or to overcome this quadratic cost, one approach is to linearize the kernel, or is to linearize the softmax, right? And one attempt of doing this is what people call linear attention, which essentially says that the exponential, so this is a dot product, right? So this exponential of dot product can be approximated as the dot product of two feature maps. And these two feature maps could be polynomial feature maps, or random Fourier features are also an approximation of the exponential kernel. There are various ways of approximating the exponential kernel with the dot product of two finite dimensional feature maps. And so if you use this trick, then the quadratic, so this is quadratic because you have a sum of a sum. If you use this trick, what you can do is that you can pull out the phi qt from the sums and rewrite this operation in this way. And now you see this, in this way you have pre-computed this term, these two terms, and then you multiply them by phi qt. Now in practice, people have observed that the normalization is useless, or at least is not very useful in terms of stability, and it doesn't bring anything in terms of learning. And people have also established, I mean, empirically demonstrated that the feature map phi can be taken to be the identity. Massive simplifications. And so if you do that, your transformer becomes an RNN. It becomes a very simple RNN with the identity update equation, right? So here is just ST is equal to ST minus 1 plus something. There is a transpose missing here, sorry. And then you have, this is just the recurrence of the RNN. And then you have the final readout, right? The standard final readout. Okay, with these two simplifications, a transformer becomes an RNN, a linear RNN, right? Here is linear. Okay, so we have, we have a parallel form, which is quadratic in length. This is the original attention layer. And we have a sequential form, which is in principle not parallelizable because it's sequential, but it's only linear in length, right? This operation here is linear in the length of X. But again, the quadratic, the original form, which is quadratic, can be parallelized, right? So the point is that if the length is not too big, the parallel form will always win, will always be the preferable one, right? Because essentially the quadratic complexity drops to constant complexity, because you can do everything at the same time using GPU parallelism. Now, a slightly more general form of the recurrent update that I presented in the previous slide of the RNN update is this one. So instead of having the identity here, you can actually multiply the previous state by a linear map matrix here using an associative operation. So this associative operation is important. It's important that it's associative. So for example, it can be matrix multiplication, that's associative, or it can be a Hadamard product. And we will see later that this is actually a useful operation to do, the Hadamard product. But anyway, you can generalize the recurrent form of transformers with this slightly more general linear update. It's still a linear RNN, right? Before it was an identity RNN, if you will. Now it's a linear RNN. It's a generic linear RNN. Now, the point is that if this operation is associative, then you can use something called parallel scan, which is an algorithm that has been around for 30 years, but it has been rediscovered by the deep learning community recently to parallelize RNNs, which are associative. So if you have a nonlinear object, then you can't do that. But if you have a linear object and the operation is associative, then you can use this algorithm to drop the complexity from L to log L by parallelizing. Now, the problem with this approach, even if it can be, so you might say, okay, now you can parallelize the recurrent form, and it's already linear in L, so you win. So this should be the preferred approach, not the parallel one. The problem is that this approach, what it does is that it requires to materialize the ST matrix. So, you need to compute the ST matrix and materialize it in your computer for each time t. And the matrix ST is big in principle. And so from a memory standpoint, this is a problem. This is a very memory hungry approach. Okay. And of course, when you actually do and implement these operations on a CUDA kernel or on a Triton kernel or whatever kernel you want to use, if you need to, transfer data in and out of memory, you're going to end up being slower than if you didn't try to use these sort of smart tricks. So actually memory, if it's very, heavy, it will slow you down. So it's not just about complexity. Memory is a key part of accelerating deep learning architectures. Okay, so moving on. So linear attention that I've just presented works fine, but it works less well than the standard parallel, the standard full attention. that I've started the talk with. So in order to overcome this sort of gap in performance between linear attention and the full, attention, people have introduced, alternative models. For example, gated linear transformers. I don't know how famous these are, but state space models nowadays, these are quite popular, right? Things like S4 or Mamba, okay? So these are linear RNNs, okay? Associative RNNs of the same form as before, this one, where the associative operation here is cheap. It's not a full matrix multiplication because that's expensive, but it's cheap. Like, for example, you see here in state space models, the associative operation is Hadamard. So it's pointwise multiplication. So you see, this is cheap to do. Now, these SSMs have shown quite good success, but they're still not on par with, at least empirically, with the original transformers, especially for long context tasks. And so one of the alternative, the most popular alternatives nowadays to these SSMs. So the reason is because the reason intuitively is because this associative operation is not as universal as the dense matrix multiplication, right? This is you're doing a compromise. This is essentially the same as using diagonal matrices. This is essentially the same as saying, let's pick A to be a diagonal matrix, and let's then do matrix multiplication. So you might, you can actually show it in the second part of the talk. We will do this more rigorously, but it's not hard to believe that if you're doing an RNN with a diagonal update, you're not going to get the same expressive power as if you were to do a linear RNN with a dense update, right? This is the reason why they're not as performing as the original ones. And a sort of compromise between a sort of cheap and diagonal update, if you will, and the dense one is this one called DeltaNet. So DeltaNet is one of the sort of state-of-the-art transformer architectures, and so it's a linear attention model where the update is sort of is cheap, but is not diagonal. So it's identity plus a rank 1 matrix. So it's low rank. Okay. So here is a sort of the idea was to somehow trade off cheapness of the operation, but at the same time not going fully diagonal, right? So this is a popular architecture that seems to work really well, and is very efficient to evaluate because we can parallelize it along sequence length using this parallel scan. But again, as I said before, the memory might kill you, right? So here, if you want to evaluate your DeltaNet using parallel scans in a naive way, what you would need to do is you would need to materialize the matrix ST, so the state matrix, at each time t. And if the matrix is big, this is very memory consuming, and this will slow you down. So the paper that we started working from is this, I give the reference at the end from Young and collaborators, very recent paper, where they essentially what they propose a strategy that trades off memory for parallelism. And the main idea is to essentially chunk the sequential operations into chunks, literally into chunks, and then say, within each chunk, I do the operation sequentially. So the memory is sort of, kept under control. And then I parallelize across chunks. Okay? And, what we did in this paper is that we tried to give a mathematical explanation of this chunking that allowed us not only to recover their approach, but also to generalize the delta net to higher rank matrices, not just rank 1 updates. So this is what comes next. And we did that going through dynamical systems. Okay, so not quite the same dynamical systems as perhaps the ones that were presented so far. So my background is in stochastic analysis, so SDEs, and the generalization of SDEs are controlled differential equations. Okay, and it turns out that all the models that I've presented you so far are discretizations. I mean, it's not too hard to see it. Are discretizations of controlled differential equations of this form. Okay, so this is a very particular form of controlled differential equation that encompasses all the models that I've presented so far. So here you see the input sequence X has been gated. This is why all these models are called gated something, right? They take the input sequence, they apply some transformation to it, and they get out two gates. And these two gates are two paths for trajectories. The trajectory W, which interacts multiplicatively with your state update, and the trajectory Xi, which interacts additively. Okay, so this is something like, yeah, if you think in terms of SDEs, you can take, this is a sort of multiplicative drift and an additive noise, if you will. Okay. Okay, rough path theory, these things, we know how to solve these things. We know how to think about these things. We have numerical schemes for these things. We know how to accelerate numerical schemes for these equations. So we can take, somehow we can leverage the the repertoire of numerical schemes that we have in order to try to accelerate these models that are just discretizations of this equation. And that's exactly what we did. And that's exactly somehow the simplest possible discretization scheme recovered what these people proposed as an acceleration solution. But we can do more, and that's what I will try to explain. So the first thing that we note is that when we have a differential equation or a dynamical system in this of this form, we can think of it in terms of a flow. Okay, so the flow of a differential equation is a map from the initial condition to the current state of the differential equation, right? Yeah. You can write down the solution at time t as the solution at time s multiplied by the flow map, right? The flow map between s and t, plus the same thing for the additive term. Okay, so the flow map is what transports you from s to t. And it turns out that for this specific type of equations, the flow map is an explicit form. There are many forms. I mean, there are many representations for this flow map. This one is quite canonical. It can be written as an infinite sum of iterated integrals of the driving path W, right? If you expand the equation by p car iteration, this comes out naturally. There is also an alternative representation of the flow. It is itself the solution of a differential equation. See, an integral equation. Here in this case, I've written it in integral form, but it's, if you differentiate with respect to t, you get a differential equation for the flow. But the flow itself is a differential equation. Okay. But now, okay, so now we have this flow representation of these dynamical systems. And so then we can simply say, okay, now we know exactly what the flow does. The flow from S to T and from T to U are completely separate. So if you want to evaluate this, if you want to numerically solve your differential equation, you can solve it between S and T first, and then T and U after, and then you can compose the two things. This is exactly the flow property, right? You can decompose flows. And this is exactly what you would do. And so we named this sort of paradigm or framework as parallel flow, which consists in the following thing. You take your interval, like your time interval, you discretize it into chunks, which is exactly what we do when you want to solve it, an ODE or an SDE. You discretize your interval into chunks. Within each chunk, you compute the relative flow. And, you can do that in parallel, right? Because, across each chunk, the flows don't communicate with each other. They are completely independent. So you can compute them all at once in parallel. And then you can use parallel scans to propagate, the initial condition as 0 through these pre-computed flows to get the final solution, right? So this is all quite intuitive once you have the flow view of the differential equation. But then, okay, so this is provides an interesting viewpoint on these computations, because you see, if the number of chunks M is equal to L, to the length of the sequence, then you collapse to the parallel computation. You do everything in parallel, you see? Whilst if the number of chunks is equal to 1, you have the fully recurrent or the fully sequential form. So this chunk-wise approach is essentially an interpolation between the two forms. It's an interpolation between the parallel form and the sequential form. And it allows you to trade off parallel computation versus sequential computations. So it's it's a good thing to tweak in order to trade off between the two words. Okay, interval selection, I will skip it. Okay, so let me give you a practical example of this. And the practical example is about delta net, right? So you remember this delta net is an RNN with this rank 1 update. We can do rank R. This is what we did. So you take your gating mechanisms, your two driving paths, W and Xi, to be exactly of this form. There are two differentiable paths such that their derivatives are the multiplication AT BT transpose for omega and A tilde T BT transpose for Xi. These are choices, right? These are arbitrary choices. They might say, why you do that? Well, because if you take, so A tilde and B are D times capital R matrices, well, are paths with values in D times R matrices. So they are of low rank, capital R. And if you take R equals to 1, you get delta net. Here it is. So this is a direct generalization of delta net, where you don't have I identity plus rank 1, but you have identity plus rank whatever. Okay? This is an example that generalizes a model that many people are using. Okay, so following on this example, a computation, very simple computation, you can write down the solution of your differential equation in this way. This is a convenient way of writing down the solution of the differential equation, because it makes appear two matrices, these are not matrices, they're like path with values in matrices, but there are two parameter paths. So these are the matrices W and U. So you can write the solution in this way, where there are these two key matrices, W and U. And W and U, they themselves solve two integral equations. But now these two integral equations are not differential equations, because you see here, that's what we thought in the beginning. These are differential equations, so we can repeat the same reasoning, but they're not, because you see here, there is an AT. So here you're solving W between S and T, but it depends on AT. So the differential equation somehow looks both in the past and in the future. There's not really a causal in time standard differential equation. These are two parameter complicated objects that you can discretize, and you get this. But now the point is that even if they look complicated, there is an easy way of evaluating this differential equation. So again, the discretized update looks like this. And the two matrices that appear, U and W, they solve these integral equations that now I've written in discrete, I've discretized and I've written everything in matrix forms. So you see that these two things are two implicit equations. You see, this is an implicit equation in W, and this is an implicit equation in U. And the M here is a causal mask, is the standard causal mask for autoregressive transformers, right? That masks the future and keeps only the past, right? So this, the update can be written like this. And as you would expect, these two implicit equations can be solved exactly by inverting a tensor, not a matrix, but a tensor. Now, in the paper that we started from, these are matrices, because if you have rank 1, these two things here are matrices. And so you can invert these matrices quite easily because they're actually tridiagonal. No, they're lower triangular. These two matrices, in the rank 1 case, you end up having these two matrices being lower triangular. And so you can invert them quite cheaply. And that's what was exactly what their paper did, and they get hundreds of citations and blah, 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 right, for that. But this is a big deal, right? I mean, sort of easy to see it once you see it, but in practice, it makes a big difference to see the computation in this way. And now, if you want to do it for higher ranks, this is what you end up with. You end up to invert, in a tensor sense, a tensor. You can use backward or forward substitution. It's okay. You can do it. But you can actually compute the inverse because of this. This is not quite lower triangular. It's lower triangular in a tensor sense, which is explained in this corollary, but I'm not going to explain it further. But it's because of this lower triangular structure in a tensor sense, you can actually compute the inverse explicitly using only forward operations, which again, they can be parallelized. Okay, so it's convenient and efficient to solve this tensor inversion computation. This is what they did, okay, just as a demonstration that these things actually do work. Here they took a chunk, I don't remember what was the size of the chunk. And then they compared the chunk-wise approach that I've just presented against the original approach. And you see, if you increase the sequence length, or if you increase the number of head dimensions, which is something within the transformer architecture, you get a bigger and bigger speed up. You see, this, the longer the sequence and the higher the dimension of the heads of the transformer, the higher the speed up that you get by doing this chunk-wise operation. So this really works. This view really works. So it provides really this sort of interpolation between the two views. This is true also for higher ranks. Okay, this is what we did. This picture remains essentially unchanged also for higher ranks. There is an alternative. We can do even better, but I guess that yeah, maybe I can skip this. There is an even better approach that I will not discuss. So let me go to the second part, which is shorter than the first part. Low rank updates are not the only parameterizations that one can choose. In a second paper, in this series of sort of finding good computational paradigms for SSMs or transformers that we have been working on, we have been looking at alternative parameterizations of these updates using sparse matrices. Okay, such that we can achieve a certain number of properties that I will try to explain during this the next few slides. Okay, so before I was sort of vague, I first sort of vaguely stated the idea of expressivity or universality. So this is a more formal definition, which is way too formal, so please don't read it. What this is all this is saying is that usually in deep learning, you have models are of this form. You have a complicated internal architecture with many parameters, that are usually randomly initialized, right? So these are, if you think about a generic neural nets, it's a really complicated combination of random matrices. That's all it is. And then at the end, you have a final readout, final layer that reads out the complicated computations that are done internally by the rest of the architecture. It's always somehow usually decomposable in this way, which is very much the same paradigm as reservoir computing, right? That's perhaps more familiar to this community. And so if you have a model of this form, what you want to see or what you want to prove usually, or not prove, but you want to make sure that if you make the model bigger and bigger and bigger, so if this n here governs the width, say think about the width of the neural net. If you let the width go to infinity, you want to ensure that any function, at least continuous function on a compact set of your data space, can be approximated in some in some sense. Here is a sort of uniform approximation statement, but it can be generalized to other type of topologies. It can be this function, target function of interest, can be approximated in the uniform norm arbitrarily well. So at an arbitrary precision, here there are random parameters, right? So this is a probabilistic statement, so with high probability, right? So you can approximate a function, target function of interest, at an arbitrary precision with high probability, and the probability is higher and higher as the width increases, and eventually it becomes 1. Okay, so this is essentially a probabilistic view or probabilistic version of universal approximation that I guess many are familiar with. Okay, so SSMs or controlled, or more generally controlled differential equations. Here is exactly the analog or equivalent statement. You have a controlled differential equation as a model or a linear transformer or an SSM or whatever. Here I've written in continuous time, so and in integral form because I want to integrate to get the solution. So the internal model is like this, and then you have a final linear readout that acts on the solution of the model, on the solution of the differential equation. And you see here, because this is a linear model, you have your vector fields, right? Here A are your vector fields, the associative operation that I was telling you about before. So these are random matrices. Here they are. And then you have your driving path W. I haven't included the Xi path just for simplicity. And here it is. So the randomness is in the matrices, but then the model is this one. Now, what we proved in the previous paper is that if this matrices here, so there are as many matrices as so this W here is a multivariate path, right? Is a path in DW dimensions. This is the results of the gating mechanism. You get a path in DW dimensions, and for each of these dimensions, you have a different matrix. That's why they're DW of these random matrices. What we proved in a previous paper is that if you take the standard initialization of the deep learning people take, so Gaussian dense matrices, you get universal, you get probabilistic universality, right? You get the previous statement. If you take this Gaussian with a Gaussian choice. This can be generalized to a more general statement beyond Gaussian, provided that you have some sort of reasonable assumption from the tail of your random matrix distribution. It's not too hard to do. Well, it's actually hard to do, but it's not too different from the Gaussian proof. It's a sort of central limit theorem type result. But then, of course, dense matrices are bad for computations, right? Because these are expensive objects. So instead, as I said before, SSMs, they take diagonal matrices. So you can take diagonal matrices, say you put a random Gaussian distribution on the diagonal parameters, and these are not universal. You can prove this quite easily. SSMs are not universal. So what they do is that they stack several layers, right? And so if you stack several layers, you can recover universality, but you cannot do it with a single layer, a single differential equation. So in the second paper that co-authored with still Nicola, Ben, Walker, Lingy Yang, and Terry Lyons, in all of the three in Oxford, we looked at three candidates, three replacements for the matrices, which are sparse. The first one is sparse. Just take sparse, particular sparsity. So you start with a Gaussian matrix, and then you mask the entries of this matrix with a Bernoulli mask that set the entries to 0 in such a way that the resulting matrix is sparse with n, with the order n1 plus epsilon non-zero entries. So you make this matrix almost diagonal, but not in the diagonal, but sort of everywhere else. You take this Bernoulli mask approach. And this is something that people do in random matrix theory, that you have results in this direction. Now the problem is that, okay, this induces a very unstructured sparsity on the matrices, right? Because the non-zero elements are sort of all over the place. And there isn't really any, to our knowledge at least, usable JAX or PyTorch or similar implementation for sparse matrices multiplication. So it's true that in principle, these are a good idea, but it's not clear whether NVIDIA has given us a CUDA kernel that we can use yet. I'm sure that they're thinking about it, and I'm sure that it will, because of course, we're not the only ones who want to multiply sparse matrices, but for now, we haven't been able to implement this particular choice. Second choice, Walsh-Hadamard matrices. So these are matrices that essentially, these are n by n matrices that can be constructed recursively, at least in some cases. And they have the property of being mutually orthogonal in this sense. And they have entries just plus or minus 1. So these are matrices of plus or minus 1, deterministic. Here, there is no parameter. And so an alternative representation of the vector fields of your differential equation can be of this form: Hadamard matrix times diagonal. Okay. Now, this is not quite sparse, but it's not bad as an idea, because multiplying Hadamard matrices can be done in n log n using something very related to fast Fourier transform. You have an algorithm that is called the fast Hadamard transform, and is very similar to the fast Fourier transform. So you can do this. You can do matrix multiplication with these matrices in n log n instead of n squared. And so these are also a good alternative. Final parameterization, which turns out to be the best out of the three that we were thinking about: block diagonal. Block diagonal matrices with the size of blocks satisfying certain conditions. And these are the conditions. So the final result is that for these three alternative parameterizations, sparse, Walsh-Hadamard, and block diagonal, you get maximal expressivity when you let the width of the net goes to infinity. So these are maximally expressive. Block diagonal, you need to have the size of the block to go also to infinity as n goes to infinity. So you can't keep these matrices with constant block size. The size of the block need to go to infinity. Of course, much slower rate than the size of the matrix, but it also needs to go to infinity if you want to recover the universality. Right. So because of the problems that I explained before, so if you want to parallelize these operations, you want to use this parallel scan algorithm. The problem is that with sparse matrices and Walsh-Hadamard matrices, if you multiply two things of this form, you don't get, again, a matrix of that form. If you multiply two sparse matrices enough times, you might not get a sparse matrix. If you multiply two Walsh-Hadamard matrices enough times, you don't get a matrix of the same form. So the parallel scan really requires this sort of invariance, which is not kept with these two choices of parameterization. So we can't really use them to accelerate parallel computations. But the block one, yes. So the block one has really all the benefits. It's cheap, has a low number of parameters. It can be parallelized using parallel scan, and it has universality. So for some, the simplest possible thing you can think about works. So this is a summary of what I've just been talking about. So you see dense matrices, very high number of parameters and cubed. You can, these are the parallel and recurrent costs, which are high because they are dense. So it's very expensive to multiply them. There is an efficient implementation with parallel scan, true, but it's still these are high, extremely intensive. And they are, of course, universal approximation. You can do universal approximation with this choice. Diagonal, all fine, all great, but you cannot have a universal approximation, so that's not good. And then you have sparse, Walsh-Hadamard, and block diagonal. Sparse and Walsh-Hadamard are great, but you cannot use parallel scans because you lose. They are not multiplying them is not giving you a matrix of the same type. And block diagonal has all the benefits. Cheap, can use parallel scan to parallelize, so an efficient implementation, and it's maximally expressive. So here is it's a simple example. So this is state tracking. It's a typical sequence model tasks that people use to as a toy task to compare their different transform or SSM architectures. This task is very simple. You take permutations, you compose permutations, and you want to get the final permutation, the final object. This is just multiplying permutations and get what happens at the end. And so if you have enough factors in this multiplication, models are not able to do it, sequence models. And so you see here, all these models here, if you increase the sequence length, so if you increase the number of multiplied permutations, you need more and more layers for this type of models in order to achieve a 90% accuracy of this state tracking task. And these models here are all the models with diagonal updates. This is demonstrated they're not universal as they are in some sense. They need more layers. The one at the bottom here are the ones that the green one here is essentially is the same picture for the new parameterizations that we proposed. The sparse Walsh-Hadamard and the block diagonal, and also the dense matrices. Of course, they can state track because in one single layer, and you can see it. And the other two are essentially, what are they? They are LSTM type thing, but LSTM cannot be parallelized. That's the difference. So block diagonal is really the only one that can be parallelized. It is you can do state tracking, you can do everything with block diagonal. We didn't necessarily anticipate that at the beginning, but this is what came out of the analysis. And okay, let me conclude. So the first part of the talk was about parallel flow. So you can see transformers and SSM, linear transformer and SSMs as discretizations of controlled differential equations. Therefore, you can solve them using a flow representation. The flow, you can decompose it into local flows, and then these local flows are independent and you can parallelize them. So the chunk-wise operation that people use to find a good trade-off between parallelism and sequential operations is essentially just a flow representation of a differential equation. Alternative parameterization of the vector fields or of the updates that we investigated were sparse, Walsh-Hadamard, and block diagonal. They all have maximal probabilistic expressivity, but only block diagonal for now provide an efficient parallelizable GPU implementation. that is easy to use, or at least that we have been able to use. Yeah, this is a final remark that I will skip. Thank you for attention.
All right. Thank you, Yuka. Thank you very much for organizing and for having me and for putting up with me as the last speaker. You know, I can tell I'd rather ask questions to the last speaker than, you know, it was great to hear. So what I'm going to tell you about is trying to learn dynamical systems from time series data with the hope of making it usable in practice. So what happens when we have noisy data and irregular samples, and how do we use modern, you know, computational techniques to set that up and make it public. And so I'll kind of walk you through some of the ideas I have for how to set up this problem and make it general. So the general framework that I'm going to look in for this talk is SDEs, but this can also generalize to discrete time dynamical systems, which you heard about from Jeroen, although you may have to make some changes depending on assumptions. But here, let's assume that there is some true SDE of interest that has a drift function f and some diffusion L, and it's being driven by some Brownian motion. And there's some initial condition out there that started this process. And then I get to see data at discrete times, tk, which may be widely spaced apart. And I don't get to see the state of the system x. All I get to see are these observations y, which are come from an observation operator h, which may obscure some information in my state x. For example, maybe it picks out the first coordinate of my state space. And then there's some additional noise that happens with my sensor, right? And so I collect this capital Y measurements from time 1 to time k. This is sort of like a noisy time series that you get in the real world. And then the first line is sort of my modeling assumption that I want to project my data upon. And of course, as I mentioned earlier, you can also make a modeling assumption that has a discrete time noisy process as well. And a lot of the stuff that I'll say will hold. And so my goal then is to define sort of all of the parameters that underpin my system of interest. I'm going to call it theta, which means there's some initial distribution that started my process, and there's some drift function I may not know about. There's some diffusion coefficients out there. There's an observation operator H that I may or may not know. There's some noise processes, et cetera. And what I'd love to be able to do, I'm not promising that I'm going to do this for you, but what I'd love to be able to do is recover all of these things in principle from the data Y. Okay, and why do I want to do that? I mean, we're all kind of at this conference already, so we're passionate about learning dynamical systems, but the two reasons are really to understand how the system works that the data were generated from, and then to also be able to predict the future of the system. These are kind of two fundamental goals in science and engineering. What makes this hard? Well, the models are often nonlinear, and I might not know what they are. The data, again, they're noisy and they're finite, and they're obscuring information about the real system. And there's some large unidentifiability questions and huge model equivalence classes that could give rise to the same data sets. And in particular, it may be difficult to even find a single good theta, a single good system configuration that matches up with my data. That's like one problem, right? That's often one of the inference problems that we look at. But then on top of that, even if I were to find one good theta, there may have been many of them that are actually consistent with my data, right? So this is another problem on top of that I want to maybe acknowledge, that there could have been another model that was also good. Fortunately, I'm going to take the angle of Bayes' rule may save us from some of this stuff. And in theory, it ought to. What does it say? It says that if I have a prior belief over all of these parameters and functions theta, then the posterior, the probability of a particular theta under my data observations is proportional to the likelihood times the prior, right? And what this means in practice is that maybe I can obtain some distribution of functions or parameters that correlate and together answer the questions in the top two bullets. So in other words, so how would they answer the top two questions? So for example, the first one of identifying a single good theta would correspond to maximizing my posterior. Just find the favorite one, right? And then under limited data, many choices of theta are consistent. this would be consistent with identifying a posterior distribution of all of them. Okay, so how do I get a likelihood for the setting that I just showed you? How can we obtain or approximate a likelihood of data yk given theta? The answer, in short, is to solve a bunch of integrals, and there are algorithms for doing this. Some of them are just quadrature, and some of them live in, the sort of one of the terms for this is data assimilation, and these things that relate to filtering algorithms like Kalman filters and nonlinear Kalman filters, particle filters. So I'll go into one algorithm and try and explain how that works to you. But the idea is that if you run one of these algorithms, it will configure it at a given theta. It will tell you the likelihood of the data. Now, on top of that, how can we find a single good theta? Well, what I can do is I can take the likelihood, which gets defined by a data assimilation algorithm, and I can just optimize it. If I want to get a maximum likelihood estimate of my parameter, then I need to have a likelihood function and I need to maximize it. So it's two steps. I'm going to do optimization using the likelihood defined in one. And what's fun is that while this is a classic principle, we have opportunities now to do this a little bit better than before. And what do I mean by that is that a lot of times, especially in high dimensional parameter spaces, having gradients of a loss function can really help us in an optimization. But having the gradient of the likelihood for defined as a data assimilation algorithm, that's pretty hard to write down or derive. But fortunately, we have these auto differentiation tools, and so that may accelerate our optimization. And then, okay, how can we characterize our uncertainty over thetas? Well, the simple thing you learn in statistics is if I have a likelihood and a prior, then what I'm supposed to do is MCMC, right? I run Markov chain Monte Carlo. And again, that's a classical idea for this problem. But again, we may be able to benefit from some of the new auto differentiation packages so that when we have differentiable likelihoods and priors, what that means is we can use MCMC methods that are accelerated via gradients. So they don't just propose a thing and accept, reject. They actually look at the curvature of the space to be more efficient. And that can help us get places faster. And then also, I think we've heard a lot of this week, and I think this is really great to be talking about, is how can we leverage different kinds of expert knowledge? So we just saw about, preserving energy with Hamiltonians. We've seen that show up as we should learn a Hamiltonian, or we can also, there have been a variety of approaches to this. So I'll talk a little bit about some hybrid models, some physics-based priors, et cetera. But we should all be thinking about how to incorporate all of the knowledge that we can into our systems. Okay. And so what am I kind of pitching here is that I want to take classical algorithms that are in textbooks, apply them to these types of problems and code them up in modern methods like JAX, where we have auto differentiation of pretty much everything. But then lift these classical algorithms to new settings where, for example, my drift function can be a neural net or a Gaussian process or any combination of mechanistic and data-driven terms. So I can get really flexible with it. And the sort of fusion of this is a package that me and Inigo Urteaga, who's at the Basque Center for Applied Math, have been working on that allows us to do some of these things. And so I'll show you a little bit of that. And then once we have all of these things set up, I think that one of the big questions that I'm excited about is how do we do uncertainty quantification? How do we characterize the distribution of possible thetas efficiently that can explain our data? Okay, so I want to tell you about data assimilation. So data assimilation is a suite of methods for connecting models of dynamical systems to the data that they purportedly generate. What do I mean by this? Well, I'm going to give you a classic example. I actually pulled these slides from my thesis defense, so I apologize for some of the difference in notation. So here we're going to have a discrete time dynamical system given whose iteration operator is psi. So we take some state Vj, we flow it through the map psi, and then it gets some noise Cj. Okay, so that's our dynamics model for V. But then we collect data, just as kind of as I alluded to earlier, to data Y, which in this case is just a linear projection of my state V plus some, again, observation noise eta. Okay, and then we assume a little bit more probabilistic structure here with some Gaussians. So my initial condition is Gaussian, my noises are Gaussian, and bunch of things are independent from each other, okay? And so what does data assimilation try to do? Well, it typically aims to solve what's called the filtering problem, which says, if you give me data from y1 to yj, where do I believe my state v is at the current time j? So I have data up until today, where do I believe my system is? And this is always going to be conditional on psi and the noise distributions. In other words, you can think of the theta that I was talking about, the drift function, the noises, et cetera. Those are all fixed in this case, right? And so when you fix all of those, data assimilation is going to provide you with a filtering distribution. Similarly, it can also help you perform the prediction problem, which says, if you know how the system works and you give me data up until today, where is the system going to be tomorrow, right? And these are the type of algorithms that underpin things like weather forecasting and robotic control and all this stuff, right? Okay, so let me give you an example of an algorithm that can work for nonlinear systems. For linear psi, the Kalman filter gives you the optimal solution to this problem. But here's an example of a algorithm that works for nonlinear systems. So here we start with some initial ensemble belief about my state Vj. I told you we have to assume some initial condition distribution. So I start with some Vj, and then I'm going to flow it, and I'm going to have a bunch of particles on that distribution, okay? And for each particle, I'm going to index them with n. I flow each little particle of my state space through my dynamics operators psi, so I get some predicted location on a Vj plus 1. So now I get a forecasted distribution of particles or ensemble members, and I can compute their mean and their covariance. And so that's what this V hat j plus 1 is. It's an ensemble-based prediction. So this is a way to compute the prediction distribution that I mentioned. But how do we do filtering? Well, the idea is that you want to reconcile the predicted distribution, which is this Vj plus 1, with data that we observe at that same time. So I'm kind of writing that data as this green star, yj plus 1, right? So that the data may disagree with the mean prediction. And so how do I reconcile this? I believe my model, but also I believe my data. Both of these things have noise in different senses. So what's my optimal update into a new, what's called filtering distribution? Well, the update is given by a set of equations that relate to the Kalman gain. Basically, we take into account the spread of our forecasted particles to have some notion of our uncertainty there, our covariance, and we combine that with our assumed measurement noise and compute a gain matrix K, which essentially tells me how much to trust the measurement and how much to trust my forecast, and how those things might correlate so that I ultimately update all of my particles to Vj, this Vj plus 1n on the left. I'm going to update all of my particles based on these beliefs. And then those form a new cloud, which is represents my filtered distribution. So where do I believe the state of my system is today, given data up until today? These particles now represent that, okay? And so this is a common algorithm that would be applied when you know how the system works. You know all of the system parameters. But what happens when we don't know the system parameters? Well, let me go back to what a likelihood is. So here, I'm writing down actually a negative log likelihood. So here I have the probability of all of my data given the parameters theta. And first, I'm just using like law of total probability here to expand out this sum. Not even like independence. This is just taking one little yk conditioned on the previous guys. Okay. So this is going to be used. We'll circle back to this. My goal is going to be, can I compute each of these elements in these sum? And what it turns out is that these Kalman filters let me do that. Okay. How? Well, it turns out that if I take this term in this sum and I factorize it as an integral, I have two key parts. I have an observation distribution. So where is my measurement given the state? And then a prediction distribution. Where do I think my state is given all of my past information? And then I integrate over all possible previous states weighted by this prediction distribution. And so that gives me this, what's called this term in the likelihood. So then I want to drill down and say, well, how can I get these two things inside of this integral? The prediction distribution I'm writing this as an integral, but you can compute it with the algorithm that I mentioned before. That was the first part, right? I propagate my particles forward in time. So that's how we can get a prediction distribution. Of course, it is conditioned on my previous filtering distribution. So how do I get a filtering distribution? Well, it's a recursive algorithm. So basically, I get my filtering distribution from the past prediction distribution and some update from data. And that's kind of the story here. And so basically, this provides a recursive algorithm for computing the likelihoods. I won't do the full derivation here, but this is the idea. So if I run, for example, ensemble Kalman filter through my data sequentially, each prediction, its error contributes to the overall likelihood. Okay, and there's a very nice paper that derives this specifically for the ensemble Kalman filter by Daniel Sanz Alonso, Becca Willett, and Yiming Chen was the first author at Chicago. So it's called auto-differentiable ensemble Kalman filters, but the derivation has nothing to do with differentiation. It's just how do we approximate integrals with Gaussians and things like that. Okay. So, so that's, for example, one of these like little classical algorithms that I'm referring to that will allow us to get approximate likelihoods. Am I doing on time? Now, how can I run this in practice? So I think my next slide is just some experiments. Yeah, okay, great. So now here's an example problem that I'm going to try and solve with this approach. So say that my data are going to come from the Lorenz 63 system. It's a 3D ODE, but in this case, I actually make it an SDE. So I define my drift F as these three polynomials, right? I fix my diffusion coefficient L, and I declare that I know that my observation function is I get to see the first coordinate. And then I'm going to add noise to it, and all I know is the law of that noise. So what I'm going to get are, oh, that's just what it does. It spins around in a tractor. So if you focus on the left side of this slide, the first column here are like the real data, right? I get x1, x2, x3. But then what I observe are only these black dots in the first component over some time window, right? And so what I told you is that if I take the data on the right column here and I run an ensemble Kalman filter configured with a particular theta, then I can get a likelihood. Now, what's the theta here? All I wanted to do in this case, to keep it real simple, is I say, can I learn sigma, rho, and beta? This is a classical problem. Can I infer the three parameters of the Lorenz system from some partial noisy data? Okay. But the key is that those three parameters, which are my theta in this case, configure my ensemble Kalman filter. So I run the ENKF with those three parameters. That gives me a likelihood. Now I can compute a derivative of that and start optimizing. Okay, and so that's what I do here. So I try to minimize that negative log likelihood to get a maximum likelihood estimate. And so here I'm showing you the path of gradient descent through the parameter space, trying to fit this data. Okay, so and then we end up at the true parameters at the end of it. So that's good news, and this is something that people have been able to do for a long time. But this is a little bit faster because we get gradients, and that's nice. But also it's just good proof of concept. This is something that is giving me the right answer. Okay, now what else can I do with this though? I can also run uncertainty quantification, meaning I can run Markov chain Monte Carlo. Here I run nuts HMC on the posterior. So I have my likelihood defined with the ENKF. I have a prior, which in this case, I put a uniform prior on the parameters on a big domain. And then I run the sampling algorithm, and it generates samples for me from the posterior. And here you can see the distributions of this three-dimensional posterior. So in other words, how sure am I about sigma, rho, and beta? Well, this articulates how sure I am under these data assumptions and under my prior, which was uninformative in this case. And then once you have these distributions of parameters, you can actually generate, this kind of implies an ensemble or a distribution of functions, right? There's a distribution of drifts for every sigma, rho, beta. There's a drift function, right? And then you can think of that as its own model, and then think about an ensemble of models that together make forecasts. And that's what I'm plotting here. So this is sort of a posterior predictive distribution over uncertainty and parameter inference. So that's what these blue bands are when I'm testing. As you can see now that when I diverge from the data here around this point, I don't just give up and give you crap. I actually start to have a widening cone of uncertainty. You notice that it's small initially, And then it gets bigger when it realizes it just doesn't know where the system is. Okay, but now this is for if I already know everything about the system, like I know it's only 3 parameters and that's my only job, right? What if it gets a little bit harder? So here, let's say that actually, I don't know that it's 3 parameters, but I'm going to hypothesize a class of models. Here, I'm going to hypothesize a class, a dictionary of library terms. So here, like a bunch of monomial terms, x1, x2, x cubed, etc. And this is very common in methods like SIND, sparse identification of nonlinear dynamical systems, where people like to posit a set of basis functions, right? And then try and learn the coefficients to those basis functions. And in this case, it's common to also have a prior belief that the real system, it has a sparse set of coefficients, meaning only a few of these terms are important at all, and most of them don't show up in my equations. There's this like prior belief that physics is simple, and therefore my coefficient matrix is also sparse. Okay, and so all I've done now is instead of learning sigma, rho, and beta, instead of theta being those 3 parameters, now theta is the coefficients to this, this matrix W. In other words, the theta is the W matrix here. And then I run exactly what I just told you about, this time on full observations, but still with noise and irregular measurements. And then I plot here in the colors which coefficients I've learned and what their values are. And so what this is showing is that basically we're recovering a lot of the structure of the original system, and we're killing off the right terms and we're keeping the right ones in the right magnitudes. And this is something that like people who do SIND often show plots like this. And the advantage of what I'm showing here is that we can do this under very irregular measurements and noise, which their methods tend to fail in. Okay, but what's an even worse situation is if I know nothing about the problem. I don't even know about monomials. I just know that there's some function f that maps R3 to R3. Okay, what do I do now? Well, one idea is maybe I call it a neural network, and now my theta becomes all of the parameters in the neural network, right? And now I can apply the exact same workflow that I just told you about, just a different drift function. It's defined by neural net parameters, and now I can optimize the same guy. And here I'm showing that I optimized it because the curve is going up, things are getting maximized, and the data are getting fit. I can also run MCMC over the neural net parameters. And this would basically correspond to a Bayesian neural net, which has its own problems, and I'll get to that. But what's interesting here is that for each parameter sample that I've generated in MCMC, that implies 1 neural net, right? And that neural net I can evaluate on short-term forecasts here and generate an ensemble, but I can also evaluate each of those neural nets for their long-term forecasts, right? So I can just make a long-term forecast with that neural net to try and simulate the invariant measure for my system. And that's what's plotted in one of these blue curves is 1 neural net, the histogram over a very long trajectory, okay? And in black is the true invariant measure for the first component of the Lorenz system. What we see is many of these neural nets give us systems that have invariant measures that are quite similar or close to the real system. And some of them give us this spurious type of behavior where probably they got focused on a 1 periodic orbit on one of the lobes of the neural net. So that's what some of these KDEs that have peaks here correspond to. And on finite data, it may be unclear which of those is the right answer a priori. Maybe it spun around on a few lobes, but the reality is it spends all of its time on 1 lobe after a long time. That's possible. So hard to say. But what bothers me about this? Well, one thing is that here, especially with neural nets, the latent states are entirely arbitrary, meaning, I only observed 1 coordinate, and I'm inventing 2 other missing coordinates. And then the neural net's job is to learn dynamics on those 2 missing coordinates. And you can see what it invented. It invented these little blue trajectories, which have a different scale and location from the real system. And that's okay in principle, but it definitely means that I shouldn't be trusting much about those latent variables themselves, right? They're a bit arbitrary. Another thing is that, I said I ran MCMC with a prior over neural network parameters having a Bayesian neural net, but that's not a very meaningful prior. In other words, what prior distribution of functions did I really imply when I did this, it's very unclear what those are and whether I wanted that prior, right? And so there are other methods that allow you to be much more explicit about priors over functions. And one favorite class of models are Gaussian process models and kernel methods, where we have both really high expressivity, but also we get to explicitly specify a prior over our function class. So if I choose a kernel like a radial basis function with a length scale, now I'm saying what kinds of functions I believe are present and which ones are not. And to make it kind of compatible and parametric with the formulation that I've presented so far, we can think of choosing some kernel to put a prior over my drift functions f, but then doing some kind of basis expansion for that function f. So here, a Jeroen and Loeb expansion of the GP. And so what you end up having is a bunch of coefficients and eigenfunctions. And the idea is that as capital M, as my expansion goes to infinity, that I converge to the real function. But in practice, maybe it's enough to just have capital M modes representing this function. And this is a common strategy in inverse problems in general when you're trying to put a Gaussian process prior over some spatial field and you want to recover that field. A lot of times you just put finitely many modes over it and learn their coefficients. And so that's what we try and do here. I just try and learn these coefficients AM. The eigenfunctions are defined by my kernel, as are the priors for these A's. So at the end of the day, you can kind of rewrite this problem so that all I have to do is learn a bunch of coefficients that all have a unit Gaussian prior. And what we found for the system I was looking at here, this was the Fitzhugh-Nagumo, that in doing this and optimizing, again, the same likelihood as before, playing the same game, but with just different function class and parameters, that we can accurately recover the drift. And I also looked at some uncertainty quantification methods like Fisher information, which can be very easy to compute in this paradigm, but I won't describe too much about that. Another question is, again, how can we incorporate even more physical or mechanistic knowledge? Certainly we've heard a lot about Hamiltonians. I think if you believe your system is Hamiltonian, you should put it in the architecture within this framework, like we were seeing yesterday. But here, I had a collaboration with some folks who work actually in a clinical setting. So this is some real data for once. So we had data collected from people with type 1 diabetes. And the key is that data are quite sparse and noisy, and they're actually collected by the individuals themselves. So it's a very uncontrolled environment. Sometimes they forget to record things, all this stuff. They're wearing sensors. And we wanted to be able to give them predictions about what is going to happen to their blood sugar when they exercise, when they eat this apple, et cetera. And we wanted to make that actionable in short term. And so we knew that because we had such limited data, we needed to incorporate as much of our prior knowledge as possible. And in this case, what that means is looking into some mechanistic models that have been developed for glucose insulin dynamics. People have actually worked really hard in laboratory settings to build like physiologic models for how this stuff works. Now, what we found is that those models are not perfect, so we need to do better. And so that's why we kind of build what we call hybrid model architectures, where maybe you blend in different ways a mechanistic model, for example, some set of ODEs, or maybe a reduced order model that you derived by hand if you're doing some physics stuff. But you recognize that that's not the whole story. And so maybe you need what some people call a closure term, right? And so here, for example, we had a neural network represent a closure term for the model. There were some other ideas, and so I'm kind of glazing over a lot of these ideas, but the point was that we looked at what we called a zoo of hybrid model architectures. Any idea you might have for how to blend some physical knowledge into your architecture, try it, right? I mean, in practice, we just don't know what's the right thing to do. And what we found was, so we compared purely mechanistic models and some purely black box models like LSTMs and transformers, and then some hybrid things that used like some neural ODEs combined with the mechanistic models. And we found that those hybrid models performed quite a bit better than the purely mechanistic model or the purely black box model. And there's much more that folks should be looking into this. I mean, I think there are big questions about how do we know what kinds of hybrid architectures to pursue and when. Okay, what else? And I guess maybe the takeaway from this is, I don't know, I keep having these Caltech slides because it's like the last time that I set up my overleaf to work or whatever. But yeah, because I'm not at Caltech anymore. But yeah, like I think the kind of takeaway from those slides and some things that we've heard this week is that machine learning is awesome if you have enough data and it's good enough. On the other hand, you know, physics-based models are kind of all you need if you know how the system works and you have enough compute. But the place we're all in right now, and I think the reason we're all working on this stuff, is we only have a little bit of each. We have some data and we have some knowledge, and we're trying to blend them judiciously. And I think that's like a lot of our tasks right ahead of us right now. So the reason I told you a little bit about GPs is because I was complaining about using neural nets to represent drift functions. One of my complaints was that there's no such thing as a nice prior over neural nets, so I don't know what it means. The other thing I can complain about is that these latent states that I learned are kind of arbitrary, right? And you can see that by these little blue tubes that it decided were the appropriate, you know, location and scale for the latent states. What can we do about that? What can we do about understanding or maybe factoring out these equivalence classes of dynamical systems, right? You can imagine shifting those latent states and it shouldn't have mattered, right? It probably could have learned something else. Well, let's take a really simple example and see if we can work from there. So let's study just linear dynamical systems. Here I put it in discrete time. So I have an update equation on the right that says, you tell me my state, I evolve it by this matrix A, and then I add the control with the matrix B. So the control is U. And then I get data Y that comes from some observation matrix C. And so in this case, I'm letting the system be 2 by 2. I have one input, which is in the top, and I have one output, which is in the bottom. So that means C maps from 2 to 1, A maps from 2 to 2, and B maps from 1 to 2. Okay. And so this is kind of the workflow. Imagine that I get to see a control sequence U and observe data Y, but I never get to see the underlying state dynamics X. Okay. Well, it turns out that there are a whole bunch of equivalence classes for these systems if I only study the U to Y mapping, right? And for example, for all Q orthogonal, the set of systems on the bottom are indistinguishable from the set of systems on the top. Okay, what does that mean? That means that if I choose a particular orthogonal Q, which I did in my code, then I can change the underlying state dynamics, but the observed data don't change at all. So in other words, I have a fixed U to Y mapping regardless of what Q I chose, right? This is just an illustration. I'm clicking back and forth and showing you the state dynamics changing, but nothing observable changing. So what this means is it's probably a bad idea for me to try and recover A, because there are A, B, and C, because together there are many of them that are completely indistinguishable just from the problem setup alone. Forget about data, just the problem setup makes it impossible to distinguish them, right? And what happens in practice is if I try to run, let's say, MCMC to characterize my uncertainty over A, B, and C, here are all the parameters in A, B, and C, and this is my an attempt at a posterior distribution of those parameters given some data U and Y. And you see there's like really intricate geometry going on here of correlation, like, you know, nonlinear relationships between these parameters. And what they're really doing is tracing out a lot of these equivalence classes that can't be identified from data. And so I've been working with Andre Brudkin, Inigo, and also Yusuf Marzouk at MIT to think about how to make this system simpler. And the real key insight is that the control theorists solved this problem for us a long time ago. And what do I mean by that? Well, what they say is that actually I can sufficiently write an equivalence class for my linear system using an A tilde, B tilde, C tilde. And there are actually a bunch of different forms of the system. I'm just showing you one of them, which is called controller canonical form, which says that this new A tilde, it's not n by n. It actually just has some alphas in it. So it has alpha 1 to alpha n in the top row. And then everything else in this matrix is like fixed. It's ones and zeros. It's just a scaffold. And then I fixed B to be ones and zeros. And then the C becomes learning. Okay, so I went from, on the top, I have n squared parameters because I have like A, which is n by n. And now my A matrix has gone down to only n parameters because I've reduced it. But again, the theory tells us that that's enough to describe this system. And I shouldn't even bother with any more of these parameters. And indeed, then we rewrite the system in terms of this smaller dimensional parameterization, theta tilde, which is totally sufficient to describe the problem. And then we run MCMC on those parameters. And that's what you see on the left is actually a much simpler distribution. And what's cool is that we can actually push this distribution back to something, a cleaner version of this guy, by just sampling over all orthogonal Qs, for example. But my question is, now, how can we lift this intuition into nonlinear settings, right? I know that this same type of, the problem that I just illustrated to you is part of the problem that I showed you with the neural networks having a particular latent coordinates that are totally irrelevant or indistinguishable from other versions of themselves. And so I want to try and kind of formulate that question for you guys, because I think it's a valuable one that will help us perform uncertainty quantification. Meaning, if I want to, so I think that there's a simple setting that has a priori unidentifiability. And what I'd love to be able to do is figure out how we can remove unidentifiable coordinate transforms before I ever touch the data. In other words, as soon as I write down my model class, can I simplify it the way I just did before for the linear case? So here's an example dynamical system, which is nonlinear, but a little bit special. So I have an update equation, which is a matrix A times a set of nonlinear functions F. So I'm also looking at deterministic dynamics and no noise. I'm making this really, really simple. And so what I'm saying is that there's this capital Y, which says you give me my A matrix. So I'm thinking of throughout this, F is always fixed. F is, for example, my dictionary of polynomials, or it's my basis expansion or something like that. So they're nonlinear, but they're fixed. And under that fixed set, if you give me an A, then I get back some data Y. And maybe a special property of this F matrix is that it probably has a permutation invariant structure to it, right? So if I have basis functions or dictionary terms, you can see how there's reorderings that can occur in my F. And so that's why I've said that F of X will be equal to some unpermutation of F of a permuted input, okay? But now what's the real question here? That my goal is to learn A from this data Y of A, but there are many B's such that Y of B equals Y of A, right? And can we stop this? How could we stop this? And in particular, what I'd love to be able to do is perhaps have a constrained space of matrices A that are lower dimensional, so that I can remove some of these equivalences. Could I, for example, find a mapping T that takes me from some lower dimensional coordinate system? Like in the case of the linear case, I went down to N. So can I have a mapping T that brings me from a low dimensional parameter representation up to the A matrix, so that for anything in that low dimensional space, there's an A that allows me to be equivalent, and vice versa. So I think this is one of the questions that I've been asked. I've been walking around the last week and a half of workshops asking people to help me with this question, because I think if we can even simplify this problem a little bit and reduce the space, the search space for this A based on coordinate transfer, based on removing some of these coordinate transformations, then we're going to make our jobs so much easier when we do all of the downstream stuff that I showed you earlier on, right? When I try and find one good parameter set, I've limited the search space, but also when I try and characterize my uncertainty, now I'm traversing my posterior space in directions of data affiliated uncertainty, not just carving out equivalence classes of my model itself, right? And so what I'd love to be able to do is fold this into the framework that I've told you about, because I think it's really important to have code that people can use. So I'm really working on that and trying to make things more usable. It also, I think, puts different methods on equal footing, so we can just compare and learn what makes the most sense for science. And yeah, so I think I'll just conclude by saying that the Bayesian statistics, I think, can offer a principled framework for learning continuous time as well as discrete time dynamical systems from potentially like real world data that are noisy, that are partially observed and regularly sampled. And also that we can leverage these modern computational toolboxes to have flexible architectures, right? I think we've seen a lot of really cool architectures the last few days. But also, you know, if you're looking at old school dynamic stuff, like we can speed up a lot of the optimization and sampling that people used to do. And another thing that's exciting, kind of as we just saw in the previous talk, is that we get free-ish or 10x cost access to quantities like adjoint or Fisher information or Hessians or any of these, you know, derivative-oriented quantities that a lot of times we write down and wish we could have. I think we can start imagining that we have those, right? And I think that's really powerful to remind ourselves that we can access them whenever we want. I think that in the context of what I was talking about here, I think it will enable a lot of new innovations in inference algorithms. So I just want to acknowledge all the folks who have helped me with this work. And of course, thank you very much again to Yuka and the other organizers for inviting me and for your attention. So here's some references and the repo that I'm mentioning. Please reach out if you want to, on one hand, like apply this stuff to your problems and try some of our tutorials, or if you have some cool new methods and you want to put them in, I'm happy to try and work with you on either of those types of things. So yeah, thank you very much.